All right, and a big hello to everybody. Welcome back to Cheg's Calculus Office Hour. Welcome to our live office hour brought to you by Cheg. I'm at Wallace STEM. You might know me from my channel at Wallace STEM, where I take trends, make them about math. I say come for the trends, but stay for the math. For those of you that have been here before and joined our live events, welcome back. But for those of you that are joining us new for the first time, the goal here today is to help you understand your calculus course, your calculus concepts just a little bit better. I'm going to be here every week to do just that. We're going to be doing today from 5 o'clock to 6 o'clock Pacific time. And then next week, we're going to move over to Thursdays at 4:15. So make sure you're scanning this QR code up in the corner so you're up to date with the schedule so you don't miss us next week for our calculus study hour. Think about this as your virtual office hour. That's right. I'm here to help answer your questions. So stick them in the chat, and we're going to do our best to answer as many of those questions that you drop in the chat as possible. In fact, last week as we were wrapping up, a couple questions came in that I didn't quite get a chance to answer. So I want to pick up with those questions. While I'm putting those questions up, stick your questions in the chat and we'll be sure to answer your questions all about calculus today for the next hour. Question came in last week about triple integrals. Now, those are more usually like a Calc 3 concept, often seen in calculus in college, but the concept behind a triple integral is actually pretty simple for any calculus student who's done integration to be able to understand. So a triple integral is exactly like it sounds like. We're going to integrate. Let's go from 0 to 1 of the integral. Let's go from 0 to the letter z. Of the integral, let's go from 0 to x plus z. And let's do 6xy. Nope, we're going to do 6xz, sorry. 6xz, and it's going to be dy dx dz. So we've got three integrals stacked up that we're going to do. And really, you can think about this triple integral as just a regular integral nested inside of another integral, nested inside of another integral. So we just have to solve them one at a time. So just looking at this inner integral, it says we're integrating dy. So we're going to integrate with respect to y. I don't see any y's. That means this is a constant in terms of y. So any constant, its antiderivative is that constant times y, our variable. And then we're going to integrate that from 0 to x plus z. Well, we know we can plug that in for the y. So we have 6xz times the x plus z. And then we'll subtract what we get when we plug 0 in for the y. Well, 0 times anything is 0, so there's really nothing to subtract. Let's go ahead and distribute this through, giving us 6x squared z plus 6xz squared. Now that's the integrating of that inner integral. Around that is another integral that's going to integrate from 0 to z, and we're going to do that dx. So let's do that next level integral. We'll go all the way out to the dx and integrate our expression. Remember now, x is our variable, so we're going to look at the other variables as a constant. So z is a constant. We're just taking the antiderivative of x squared, which is x cubed, and then we divide by 3. 6 divided by 3 is 2. Z, the constant, is just along for the ride. Here with that x, we'll increase its exponent by 1, and now we'll divide by 2. 6 divided by 2 is 3, and the z squared is along for the ride. And we're going to integrate that as x goes from 0 to z. So let's plug z in for the x. So we have 2 times z cubed times z is z to the 4th, plus 3 times z squared is z to the 4th. Which means this is going to equal, running out of space, we'll move over here. Notice those are like terms. Add them together and we get 5z to the 4th. But remember, around that integral, we've got another integral. We're integrating from 0 to 1 with respect to z. So these triple integrals look complicated because we've got this dy, dx, dz stuff going on, but really we're just taking the integral of the outside and then or the inside, sorry, take the integral of the inside and then kind of work our way out through the parentheses. Because now we're going to do this last integral from 0 to 1 dz. So we know we can increase the exponent by 1, divide by the new exponent, and integrate that from 0 to 1. Well, 1 to the 5th is 1. 0 to the 5th is 0. 1 minus 0 is just 1. What this tells us, if I've got a four-dimensional shape that's underneath the curve 6xy, its volume, which is weird to think about in 4 dimensions, but its volume underneath is going to be exactly equal to 1. It's a triple integral. It looks more complicated than it really is. I'll step aside in case you want to get a picture of that, but I also see some comments are starting to come in. If you've just joined us, welcome. I'm at Wallace Jim here on behalf of Trig to help you tackle some of your toughest math concepts, specifically in your calculus class. And we're here every week to answer all of your calculus questions. So make sure you scan this QR code in the corner so that you are aware of the schedule, because next week we're moving over to Thursdays, and I don't want to miss you when you log in with your calculus questions. We've got a question from Franman on TikTok, wants to know if one integral represents the area under the curve, does the triple integral represent the volume? Actually, the double integral is going to represent the volume. So let's take a look, see if I can draw a three-dimensional picture. Now, I went into math. Don't judge my art skills, all right? Give me some grace here. I'm going to do the best I can. Let's say we've got the x-axis, the y-axis, and the z-axis. This is supposed to be three-dimensional. So that's kind of like the corner of the room, and then if you went through the wall or under the ground or through the other wall, right? And there's going to be some curve out here floating in space. And we're going to project it down to the ground. And it's going to create, this is why you don't judge my drawings. Does that look three-dimensional? It's supposed to look kind of three-dimensional. It doesn't look too bad. So the idea is, you know, it's got this curve to it. Does that help it look more three-dimensional? Maybe. It's this three-dimensional curve. It's got some direction in the x, and it's got some direction in the y. And so when we do dx, dy, we're going to get all the area underneath this curve down to the ground. And so this three-dimensional shape that I have so crudely drawn, that's what a double integral is trying to find, the volume underneath. So a single integral, that's the area under a curve. A double integral, that's the volume underneath the curve. It also shows the total amount of change that's happened in both the x and the y direction, and adds up that total change when we're working with multiple variables. Now, a triple integral is kind of weird, because then we've got this three-dimensional shape, maybe this three-dimensional shape that I've looked at, and we want the total change that's happening in all three directions that's projected on a four-dimensional plane. It's kind of weird to think about. You heard about hypercubes and some of that. You can look that up online. That's what a triple integral is getting at. But really, when we're talking about triple, quadruple integrals, at that point, we're really just talking about some type of application, not so much a volume concept. But we've just got 3, 4, 5 variables that we're working with. They're all changing. We want to measure the total change under the curve. That is what it measures. Let's see. Can I explain the second theorem of calculus? I think you're talking about the fundamental theorem of calculus, if I'm not mistaken. Fundamental theorem of calculus is really, really important because it blends together some of the two big concepts of calculus. First, you talk about derivatives, and you spend all this time measuring change. Then you talk about rectangles and measuring the total number of area by doing infinite number of rectangles. And then we find out both of them are actually inverses of the exact same concept. The idea is that the derivative of an integral from 0 to x of some function, maybe in t dt, the derivative of the antiderivative, drop my pen, I'll have to get that in a minute. The derivative of the antiderivatives, those undo each other. It's like saying, what's 47 times 50 divided by 50? You're back to 47. So the derivative of the integral undoes the operation, and we're back to just the function, and we're going to evaluate that function at this variable at the top. Now, this works great if our variable at the top is just x, but sometimes, especially like on the AP test, got my pen back. Sometimes, like on the AP test, they're not just going to put x up there, they're going to put a function up there. And that's going to trigger the chain rule of derivatives, which we know, because when we take the derivative, the top thing goes in using this function, then we have to multiply by the derivative of that input. Remember in the chain rule, when we did the derivative of maybe the sine of x squared, we would take the derivative of the sine to get cosine of x squared, but then we'd have to multiply by the derivative of that input of 2x. We're going to have to do the exact same thing if I'm taking the derivative of the integral from 0 to the sine of x times of the square root of 1 minus t squared dt, for example. Now, this formula, the fundamental theorem of calculus, tells us that we can plug that top thing into the function because the derivative of the antiderivative is just the function. So that's going to be the square root of 1 minus sine squared. But then the chain rule needs to click in as well because we've got a sine here. We need to multiply by the derivative of that input to the function. The derivative of sine is cosine. I'm using x, yeah. And then we'd want to simplify from there if we can. For example, 1 minus sine squared, that's a Pythagorean identity. It's our favorite trig identity. 1 minus sine squared is cosine squared. But cosine squared under the square root, that's just cosine x times another cosine x. I probably should have written it here, showing all my work. And cosine times cosine is cosine squared x. So the derivative of the antiderivative of this function going from 0 to the sine is cosine squared of x. Excellent. For those of you that are logging in right now, welcome. Take a moment, tell me where you're from. I'm always interested in who's joining my live. Sometimes we've had people join us from other countries, from Brazil. I've had people join from India. I've had people join from Europe, Germany. Tell me where you're from in the chat. I'd love to see. I'm always curious who's joining us, but also tell me what you're working on in your calculus class. Remember, this is your office hour to answer your questions that you have. So drop them in the chat. I'm doing my best to answer as many of those questions as come in. One question did come in last week that I did not have time to answer. And so I have to take a moment to go back to last week's question because I told you I'm going to try and answer as many questions as possible, and I missed one. So the one that I missed was improper integrals. So I want to go back, and we're going to integrate from 0. Let's go from negative infinity to infinity of 1 over x squared plus 4 dx. All right. I keep dropping my pins. Need to get a better place to put them on here. Anyways, when we're integrating with respect to or going to infinity or negative infinity, we can't actually do that because we can't actually do math with infinity. When you do math with infinity, weird things start to happen, and we don't want to do that. So what we're going to do instead is we're going to take the limit as, we'll call this maybe a and b, and then we'll take the limit as those things actually go to infinity. So a little call out. I see somebody here from Omaha, Nebraska. Welcome, Omaha, Nebraska. I follow a lot of football. Omaha, called all the time by quarterbacks nowadays. I don't know why. Anyways, we're integrating from negative infinity to infinity of this expression. This expression, you should notice, is the tangent inverse of x over 2. It's the square root of the 4. And then we have to divide by that square root as well. And then we want to integrate it, but we can't go from negative infinity to infinity. So we're going to go from a to b, where we're going to take the limit as that top value goes to infinity of 1/2 tangent inverse of b over 2. So we can't really plug infinity in, but we can plug b in and then let b go to infinity. Then I'm going to subtract the limit as the a goes to infinity, and then we plug the a in, which is 1/2 tangent inverse of a over 2. And these each we can evaluate one by one. So let's take a look at this first one. Actually, let's draw a graph here. What's nice about tangent inverse, it has very clear asymptotes. It starts out kind of flat, comes up, and flattens back out. These asymptotes are at pi over 2 and negative pi over 2. So when we're saying this tangent inverse, b is going to infinity, infinity divided by 2 is still infinity. What is tangent inverse approaching on the in behavior at infinity? It's approaching this pi over 2 asymptote. Well, then we got to divide by 2 again, so we'll call that pi over 4. Minus, now we're going to, oops, did you see my mistake? Somebody put in the chat my mistake, because I made a little mistake here. Hello from Tucson, Arizona. Glad to have you here. Welcome, welcome. All right, my mistake is I took a to infinity, but a is the lower limit. The lower limit wasn't going to infinity, it was going to negative infinity. So let's make a go to negative infinity, which will now be this right side. So we're subtracting a negative pi over 2, which adds pi over 2. Again, we're going to divide by 2 a second time, making it pi over 4. Pi over 4 plus pi over 4 is pi over 2. So we actually have a finite area underneath this infinite curve, which is kind of interesting to think about. All right, I see some questions coming into the chat. One is about the integral of secant x dx. Let's take a look at the integral of secant x dx. That's one that often people memorize. It's the natural log of secant plus tangent. But why is it that? That's actually a more important question. Because if you understand where these integrals come from, where these formulas come from, there's a lot less to memorize and keep track of. So let's do the integral of secant x dx. And I'm going to leave a space here. I'll explain why in just a minute. So what we're going to do to make this work is we're going to do a very clever multiplication. I can multiply by 1 anytime I want. It doesn't change the value. Secant times 1 is still secant. So I'm going to pick a convenient type of 1. And the convenient type of 1 I'm going to pick is secant x plus tangent x divided by secant x plus tangent x. Because that's the same thing on top and bottom, it's going to be 1. It doesn't change the value. But look what happens when I multiply that out. We end up with a secant squared of x plus a secant x times a tangent x over a denominator that was over 1, multiplying by 1, keeps it as secant x plus tangent x dx. This is actually really nice, as much as it doesn't look nice, because I can do a really simple u substitution by making u equal to this denominator. Notice what happens when I make u the denominator of secant x plus tangent x du. Its derivative, the derivative of secant, is secant x tangent x, and the derivative of tangent is secant squared x dx. And while the order is different, this adding doesn't really matter. It's commutative. So it's going to be the same thing as my numerator. All of that's going to become my du. So really, we're just integrating 1 over u du, because the secant squared, secant tangent dx all became my du. The denominator became my u. And this is a really nice, simple antiderivative. Let's go orange. It's the natural log of u plus our constant. But what is u? U is that substitution that we just said. And so that's where we get our formula that the antiderivative of secant x is the natural log of secant x plus tangent x. That's what our u is, plus our constant, because nobody's forgetting their constants, right? Excellent. Great question. Great question. Another great question came in on integration while we're talking about, just came in from @Jack on TikTok. YT, Jack YT. We want to look at the antiderivative of natural log. And why is it what it is? I think it's x times natural log minus 1 or something like that. I don't actually have that one memorized. because it's so easy to derive, it's not worth the time to memorize. I have a master's degree in mathematics, a doctorate in education. I teach calculus all the time. I have no idea what the antiderivative of natural log is. Well, I have an idea, but I don't actually know. But we can do the integral of natural log really quickly. And that's the nice part about understanding where these formulas come from, is there's a lot less to actually memorize. And it's more about just understanding what's happening and how the concepts work together. As we solve this, I think there's several college people here in the room. Drop in the chat, tell me what you're studying in college. If you're taking a calculus class, you're probably going to a STEM field, or maybe you just love math. Stick in the comments what your major is. If you're in high school still, stick in the comments what you want your major to be. What do you want to study when you get to college? For now, we're going to integrate the natural log of x, and the way we're going to do this is with integration by parts. Integration by parts says we're going to identify a u and a dv that make up this equation. Oh, I see an aerospace. Is that aerospace engineering? That is a fascinating field to go into. It is moving really fast. So glad to see you here, Massimo. I'm probably saying that wrong. I'm sorry. But doing our u substitution, natural log of x is really the only function in there. That's going to be my u, which means the rest of the function is going to become my dv, which is just the dx. We'll take the derivative of u. The derivative of natural log is just 1 over x dx. We'll take the antiderivative of our dv. The antiderivative of dx is just x. And then we do our ultraviolet voodoo, if that helps. U times v minus the integral of v du. If you speak Spanish, I like to say it's una vaca vestido de uniforme. However you want to remember the formula, that's great. Either way, we're going to do u times v gives us x, natural log of x, minus the integral of v du. X times 1 over x is just 1 dx, which has a really nice, easy antiderivative of x. And so that is technically the formula for the antiderivative of natural log and where it comes from. Now, often I don't see it written like this. Often I see people factor the x out, and so you'll also see the derivative of natural, or the antiderivative of natural log written this way as well. It's the exact same thing with the x kind of factored out of there. All right, so keep your questions coming in. Remember, this is your live office hour. I am here every week. We are changing the time for next week, so make sure you're scanning the QR code so you don't miss us next week when we move to Thursdays at 4:15. So do make sure you're on that, because I want to help you out with your calculus class, have you returning every week with great questions to answer. One great question coming in from TikTok, a very hard AP Calc question that people get wrong. Please teach us. Oh, there's so many great AP Calculus questions. One AP Calculus question that'll often come up is they'll give you kind of some examples of points on a graph, and it wants you to estimate the area underneath the graph. For example, let's say it wants to know at certain points in time the amount of rainfall that happened, okay? So we found out, and times in, we need units, right? Times in hours, and rain is in milliliters or something. I don't know, units don't matter too much. We're mathematicians, not scientists, right? Scientists don't like it when I say that, so tell them I'm sorry. Oh, great question just came in about the tabular method. Hold on to that, we'll hit that one next. Okay, so we're gonna know maybe at 2 hours, there's 1.2 milliliters of rain. At time 3 hours, there's 1.4 milliliters of rain. At times maybe 5 hours, there's 2.1 milliliters of rain. And they'll go on and give you several points. Maybe at 6 hours, there's, or maybe we'll do 6.5 hours. No, I don't have a calculator handy. So we'll do at 8 hours, there's 3.2. Okay. The idea here is we are going to draw rectangles to estimate the area underneath this curve, because we don't know what the equation is. So what we're going to do is we're going to draw a rectangle, we're going to use left rectangles. So we're going to use these left side values. And we're going to call this the height of the rectangle. So if I were to graph this, we would have a rectangle. The height of this first rectangle would be 1.2. The width of the rectangle is the width between the input values. So in this case, the width would be 1. So we're going to call that delta x. The change in x here is 1. Now, delta x isn't always the same. Notice the change in x here is 2. That rectangle is 2 wide. And then here, this delta x is 3. It wasn't supposed to be a nice pattern like that, but that's what you get when you make it up on the spot sometimes. So the idea here is if I'm using left rectangles, the first rectangle is 1 by 1.2. The second rectangle is 2 wide, has a height of 1.4. And the third rectangle is 3 wide, and it has a height of 2.1. If I want the total area, we just have to multiply these out and add the results. 1 times 1.2, 2 times 1.4, and 3 times 2.1. Add those together. Carry the 1, 6, 7, 8, 9, 10. This would probably be a calculator question on the test, by the way, so don't worry about the arithmetic as much. But the total amount of rainfall looks like that we've changed over time is going to be 10.3 milliliters. And so that's kind of given us an idea of what's going on with the left rectangles. Now I could do the exact same problem with right rectangles. And if we did right rectangles, we'd use the right 3. So the height of 1 would, actually let's go ahead and do that and compare, because that's an interesting problem. Let's see how much air we end up with. So with the right rectangle estimate, we've got a height of 1.4 and a base of 1. So a total area of 1.4. The second rectangle has a width of 2 and a height of 2.1. And so that's going to give us 4.2. And the third rectangle has a width of 3 and a height of 3.2. 9.6. And so that's 12. Carry the 1, 10, 15. And so if we used right rectangles, we'd estimate the area underneath to be 15.2. The truth is the area is probably somewhere in the middle, because if you remember with using rectangles, the more rectangles we use, the more accurate our estimate is. And we've only got 3 rectangles going from 2 to 8. That's not very many rectangles. We're going to end up with a lot of air in the problem. So that's kind of a good AP type question. It really gets conceptually at what's going on with those right and left rectangles. All right, so Freaky on YouTube, I promised you we would hit the tabular method of integration. It is one of my favorite shortcuts and tricks. Got to be careful using it though, because some instructors don't like it. I don't know why they don't like it. I think they prefer the formula, but the tabular method actually works excellent, especially when we have to do integration by parts multiple times. Let's say this problem. The idea of the tabular method or the table method Freaky on YouTube is asking about is we're going to take the derivative of one of the terms, maybe, or one of the factors, maybe x cubed, and we'll take the derivative all the way down until the derivative ends up being 0. So x cubed's derivative is 3x squared, whose derivative is 6x, whose derivative is 6, whose derivative is 0. Then we'll take the antiderivative, or the integral, of the other side. So e to the 2x, her antiderivative is 1/2 e to the 2x, whose antiderivative is 1/4 e to the 2x, whose antiderivative is 1/8 e to the 2x, whose antiderivative is 1/16. Notice we have to divide by 2 each time to account for that exponent. The way the table method works, it's really slick, is we get our u times v, and then we want to subtract the integral of v du. But then its integral becomes u times v minus the integral of v du. And that kind of creates this diagonal, starting with a positive and then subtracting. That maps out my answer. So mapped out, my answer is x cubed over 2 e to the 2x minus 3x squared over 4 e to the 2x plus 6 over 8, that's going to reduce to 3/4 e to the 2x, minus 6 over 16, that's going to reduce to 3/8 e to the 2x. Don't forget the plus c, and we've got our entire thing. This method technically works on any integration by parts problem. There's just a couple things that might happen different at the end that you have to watch out for. So I usually recommend to only use it when I know one derivative is going to go to 0 because it's pretty straightforward. It does work in other times, but you've got to watch out for a couple special cases. All right, we got a lot of great questions coming in. Keep those questions coming in, and we're going to do our best to answer as many of them as we can. I saw a question from @Guitarist Miguel on TikTok on the precise definition of a limit. So let's take a look at the precise definition of a limit. The idea of the precise definition of a limit is we define the limit as x approaches a of f of x is equal to some limit L. And a lot of the times we start out talking about a limit kind of abstractly. We say, okay, that means when x gets close to a, what does y get close to? Well, that's not very precise because there's a little bit of opacity. What's the word I want there? I don't know. It's not clear. And so to make it more clear, we say this is true if and only if for all epsilon greater than 0, there exists a delta that's also greater than 0, such that 0 being less than the absolute value of x minus a, which is less than delta, implies that the absolute value of f of x minus L is less than epsilon. And I think one of the reasons why mathematicians love this precise definition of a limit so much is it looks like gibberish. But if you understand what it's saying here, it's actually drawing a box around our limit. And as that box gets smaller and smaller, we're going to get closer and closer to our limit. Let me draw a picture, show you what I mean. So I've got a picture here. And here is some curve. Oh, I don't like that curve. That didn't curve where I wanted it to curve. Let's say there's my curve. And right here in the curve, there's a hole in the curve. The limit at that point we know is that y value because the limit doesn't care what's happening at the point. It just cares what's happening close to the point. And so that's the idea we're going to get at, is we're going to have some x value. And we're going to move a in each direction. So this is x plus a, and this is x minus a. This distance is going to be less than the delta. So actually, I want to subtract delta, not a. I'm going to go less than this distance here, which means it's going to give me a y value over here, where this is actually my limit. And that limit is going to be less than an epsilon away from this top value. So this is the limit plus epsilon, and this is the limit minus the epsilon. And so what it does is it creates this box, and we want delta to get really small, creating smaller and smaller boxes, which makes epsilon really small, creating smaller and smaller boxes, and it zooms us in on that point. That's what it's saying. That's what this fancy lettering is saying. But what is it? What are we going to do with that? We're going to use this definition to prove a limit. We're going to prove that the limit as x goes to 3 of 4x minus 1 is equal to 11. We've got this. We need to show the other part. We need to show for all epsilon greater than 0. So we need to let some epsilon be greater than 0. There exists a delta. That means I can choose a delta. Does choose have 2 O's or 1? I always mess this up when I do proofs. Somebody put in the chat, let me know if choose has 1 O or 2 O's. We'll fix that later if I need to. We're going to choose a delta that's equal to, well, I don't know yet. We're going to pause on that. But this delta is going to work such that the absolute value of x minus L, the absolute value of x minus L, let's assume the absolute value of x minus my limit, x minus 3, is less than the delta. If that's true, it has to also imply that this other side is true. In other words, the absolute value of my function, the 4x minus 1, minus my limit, minus 11, needs to be less than epsilon. That's what we're going to hopefully find out. Well, it's definitely equal to the absolute value of 4x minus 12 by just combining like terms. Both of these numbers have a common factor of 4. I'll factor out the 4, which leaves behind x minus 3. But I already know something about x minus 3. X minus 3 is less than delta. So this is less than, replace the x minus 3 with a delta. Well, I can choose any delta I want. I just want the answer to be epsilon. So I'm going to choose delta to be epsilon divided by that 4. And if that's true, then 4 delta is 4 times epsilon divided by 4, and the 4's reduce out, which is epsilon. So what I have done is I have shown that the absolute value of f of x minus L is less than epsilon, which is what we were trying to prove. So that is the precise definition of a limit. It is a lot of fun. Can I please show an example of integration by parts? Sure, I'd love to do some integration by parts. Let's do another integration by parts problem, and let's do it by both the integration by parts formula and also that table method or the tabular method that I showed you earlier on in today's live. By the way, if you're just joining us, welcome. We are here every week to answer all of your calculus questions here. So make sure you are not just logging in, but also scan this QR code so that you have the schedule every week so you don't miss us when we do our weekly calculus updates. So you can join us, continue to ask questions, and hopefully continue to be successful in your classes. Next week, I think we're moving to Thursdays at 4:15. So scan the QR code so you don't miss those updates. Let's do some integration by parts. Let's integrate e to the 3x times the cosine of 2x dx. Let's see if that gets too crazy. See what happens when you make up a problem on the fly. You never know what you're going to get. But that makes this fun. That's why I love these lives. You have such great questions, so keep them coming in. So this is integration by parts. We're going to make u equal to the... It probably doesn't really matter which one I pick here, as long as I'm consistent. So let's make u equal to the e to the 3x. And then the dv is going to be cosine of 2x dx. Which means the derivative of u, because of the chain rule, is 3e to the 3x. And v, the antiderivative of cosine, is going to be the sine of 2x. But because of a u substitution here, we're going to have to divide by 2. Don't forget your dx over here. And our integration by parts, the ultraviolet voodoo, or the una vaca vestido de uniforme, if you speak Spanish, u times v minus the integral of v du. So u times v is going to be 1/2 e to the 3x sine of 2x. And then I'm going to subtract the integral of, that's going to be 3/2 e to the 3x sine of 2x dx. What you might notice is the integral we ended up with is very similar to the integral we started with, but that's okay because we're going to solve it using a very similar method. We're going to use integration by parts again, but look what happens when we do it the second time. An interesting thing will happen. We are going to make our u 3/2 e to the 3x. We'll make it the whole thing. Du then is going to be 3/9. Ooh, that's nice. Dividing by 3 makes it 1/2. E to the 3x. dv is the rest of it, which is the sine of 2x dx, which means v, the antiderivative of sine, is negative cosine of 2x divided by the 2. Be really careful here with our signs as we combine these. So we're going to have u times v minus the integral of v du. This thing out front's not going to change, so we still have 1/2 e to the 3x sine of 2x minus u times v. Minus a negative is going to make it positive. 3/2 times 2/2 is 3/4 e to the 3x cosine of 2x. And then here's where people usually make their mistake. Stick in the chat, is it going to be a plus or a minus? Which do you think it is? Plus or minus? Watch your signs. Stick it in the chat. Tell me what you think. Plus or minus? I've got a negative that has to distribute through. I've got a negative from the formula. And I've got a negative on the v. 3 negatives multiplied together. If you said negative, you're exactly right. Negative integral of v du, 1/2 times 1/2 is 1/4 e to the 3x cosine of 2x dx. I am noticing, look at the camera, I can't write a straight line. That's going completely uphill, isn't it? That's okay. Don't judge me. The calculus is great. The art, not so much. But that's okay. You came for the calculus, right? Where this is interesting, or actually important to us, is this integral looks almost exactly like the integral we started with. The only difference is the 1/4. The nice part about a constant is a constant can just move outside. And this is equal to the original integral, because that's what we've been working on, the integral of e to the 3x cosine of 2x dx. Well, what I'm going to do here then is combine like terms. If this integral is over here on one side, I'm going to add it to the other side. We've got negative 1/4 of them here, so when I add it, I'm going to add 1/4. 1/4 plus 1 is going to give me 5/4. So I have not much space left. I think I can squeeze in one more line, but I don't think that's going to be enough. So let's see if I can come up here. We have 1/2 e to the 3x sine of 2x plus 3/4 e to the 3x cosine of 2x equals, when I add this to the other side, we said we'd end up with, I'm off camera, I'm still here though, I promise. I haven't left you, I'm just left-handed. Equals 5/4 of the integral of e to the 3x cosine of 2x dx. Now, we don't want to know what 5/4 of this integral is. We want to know what the entire integral is. So we need to get rid of this 5/4 by multiplying by 4/5 on both sides. And when I do, I end up with, I'll go ahead and distribute it, might as well. 4/2 reduces to 2/5 e to the 3x sine of 2x plus the 4's reduce out, 3/5 e to the 3x cosine of 2x. Of course, we need the plus c, and this is the solution to our integral. We had to use integration by parts twice to get there. And then once we had that integral, that same integral on both sides, we just had to add it to both sides, negative 1/4, so we added 1/4 of them. And then we just have to get rid of that constant that ends up in front. All right, I see some more questions coming in. That's wonderful. Keep your questions coming in. This is your office hour. Maybe I can stand over here, then you can get a picture of me with it. Screenshot. All right, I want to do the integral of the square root of tangent x dy. Is that a typo? Dx, dy? Go ahead, Jack, if you're still with us on TikTok. I need to know, is that supposed to be dx or dy? Because that makes a big difference in how we solve it. Maybe that's what you're trying to get at with your question. But in the meantime, let's take a brief aside from integration. I saw a question come in about polar coordinates. We want to know the relationship between polar coordinates and Cartesian coordinates. So let's take a look at that question. Polar coordinates actually are really convenient for describing curves and that are round, really. Anything that's round is probably easier to work with as a polar equation than it is a rectangular equation. The idea of a rectangular equation is we have split the coordinate plane into rectangles, right? This is really crude drawing, but you get the idea. Is the coordinate plane is x in one direction, y in the other direction. We only make right turns. So if I wanted to graph the point 2, 3, 2, 3 would be 2, 3, and it'd be right there. 2 to the right, 3 up. Polar coordinates say maybe it would be more useful, instead of thinking about how far we go in each direction, maybe it'd be more useful if we had a radius of some distance. And then from that radius, instead of coming out with a right angle, we came out with a circle. And so we've got a circle with radius 1, a circle with radius 2, a circle with radius 3, and a circle with radius 4, and so on and so forth. It gives us that polar grid. So I might have a point, instead of giving an xy point like we had here, now my point is going to be some radius and some angle theta. This really is going to bring in a lot of the concepts that you saw in your trigonometry class. So let's say I've got a radius of 2 and an angle of 3 pi over 4. Well, we're going to come out to a radius of 2, and then we're going to angle up 3 pi over 4 radians to get our point, which is right here. This becomes really convenient for graphing like circles, ellipses, other functions like that. But let's say I wanted to convert this polar point back into a rectangular point. What's the equivalent rectangular point that would give me that exact same point over here? Well, we've got some formulas that connect rectangular and not spherical. Spherical's in 3 dimension. What are we talking about? Polar. Sorry, my brain stopped. Polar. So one of them is the classic x squared plus y squared is equal to the radius squared. Another one you'll see is that the tangent of theta is equal to y over x. Another one you'll see is x is equal to the radius times the cosine of the angle. And that makes sense because we know x is the cosine is the x coordinate, and y is equal to the radius times the sine of the angle. These 4 formulas should be able to allow you to move back and forth between radius point, or I keep wanting to call them something different, between polar points and between rectangular points. So for our point, if I wanted to figure out what x is going to be equal to the radius, which is 2, times the cosine of the angle, which is 3 pi over 4. And y is going to equal to the radius times the sine of 3 pi over 4. What's nice is we know each of these values. The cosine of 3 pi over 4, cosine's the x coordinate on the unit circle. We're going backwards, root 2 over 2, and we're going up, root 2 over 2. So cosine the x is negative. When we multiply by 2, the denominators reduce out, so I get negative square root of 2. Sine's the y coordinate, which is positive, but multiplying by 2 reduces out the 2's. And so in rectangular, if I call this a spherical point, in rectangular, negative root 2 over 2 root 2 in the rectangular grid is the exact same point. And so I could go negative root 2, which is about 1.4, plus root 2, which is about 1.4, and that would be the exact same point on this polar grid. Excellent. Lots of great questions coming in. Let's see. Oh, so many good questions. Where do we start? Let's start with Matthew. I love that name, Matthew. I think you want me to integrate e to the x over the square root of 1 plus e to the 2x. That is a great example to take a look at. And then after that, we'll come back and do some of the other questions I saw about things like series and understanding area under a curve and why is that the integral. Great questions. Like I said, this is your office hour. We're answering as many of your questions as possible. The first question, though, that I wanted to hit was the integral of e to the x over the square root of 1 plus e to the 2x. This is a great example of where u substitution is going to come in very nicely. I'm going to change this so it's 1 plus u squared, which means I want the e to the 2x to equal u squared, which means u, its square root, is just going to be e to the x, and its derivative is also e to the x dx. Didn't leave no space. Because this is set up for a really nice trigonometric substitution. I hope you didn't mean that to be a minus, because it'd be really, really nice if that was a minus. But let's see what happens when we make this substitution using the way you've got it. So e to the x dx, that becomes my du. And then we've got the square root of 1 plus e to the 2x becomes u squared. When I've got a sum of perfect squares underneath the radical, we can solve that using trig substitution, where I make my variable equal to the tangent of theta, because we've got a nice trig substitution that's going to come out of that. So the derivative of tangent is secant squared. And so now we've got the integral of 1 over the square root of 1 plus tangent squared. Du, well, du is secant squared theta d theta. What's really nice about this denominator is 1 plus tangent squared is one of our Pythagorean identities. 1 plus tangent squared is secant squared. Oh, this is going to come out really nice. Because we've got secant squared under a square root. When we take the square root, we just get secant. And secant divided by secant, that can reduce out. And so we're really just integrating the secant of theta d theta, which we know is the natural log of secant plus tangent plus a constant. Now, these have thetas. We don't want thetas. We can change thetas to u's and then u's to x's. First, to do that, though, we need a triangle to represent this tangent of x relationship. Tangent is opposite over hypotenuse. Oh, no, it's not. Tangent is opposite over adjacent. So the opposite is u, the adjacent is 1, which means this side is the square root of u squared plus 1 using the Pythagorean theorem. So when I substitute back secant, that's the reciprocal of cosine, that's going to be the hypotenuse divided by the adjacent. It's the square root of u squared plus 1. Plus tangent. Tangent is opposite over adjacent. That's u plus our constant. All we have to do then to get from here to our final answer is go back to our e to the x. And so for my final answer, we've got the natural log of e to the 2x, when we square e to the x plus 1, plus u, which is just e to the x, plus a constant. And that was a beautiful problem. Thank you, Matthew 1, for asking that question, because we had to do a u substitution to set it up to do a trig substitution and then substitute all the way back. Excellent. Lots of great questions coming in. Like I said, we are going to try and answer as many of those questions as possible. Let's do kind of a theory question from Solaris on TikTok, asking, why is the antiderivative of function equal to the area under the curve? Why is that? Well, geometrically, let's look at what we're doing when we take the antiderivative. So here's a graph. We're going to put a curve on it. Some curve. And we're going to be really interested in what happens between A and B of this curve. Well, the problem is, if I draw lines here, this shape here that I'm trying to get the area of, we don't have a formula for the area of that shape. There's no geometric formula for that area. And so what we say we're going to do is we're going to move over a little tiny distance. We'll call that delta x. And we'll draw a rectangle. And then I'll move over that same delta x. And we'll draw a rectangle. And we'll move over that same delta x. And we'll draw a rectangle. And we'll move over that same delta x. And we'll draw a rectangle. And so I end up with 1, 2, 3, 4 rectangles in this example. Those rectangles are approximately equal to the area between A and B. And so what we'll do is we'll add up. That means we'll take the sum. We'll add up as I goes from, boy, I hope I get this notation right. Oh, as I goes from 1 to 4, because there's 4 rectangles, we're going to take the width of this rectangle times the height. Well, the height is delta x. The height is in delta x. The height is the function f of x. So f of x sub I star, depending on your book's notation, something like that, times the width, which is the delta x. And that's going to give us base times height plus base times height plus base times height plus base times height, the 4 rectangles. The problem is that's going to give us the error because this is outside, this is outside, this is too much, that's too much. There's a lot of air in there. And so what we do is we say we're going to take some number of rectangles and we're going to take the limit as the number of rectangles goes to infinity. Because if I drew more rectangles in here, I would get a more accurate approximation of that area. And more rectangles gets me more and more accurate. And so the limit of the sum, all of that becomes my integral going from A to B. Maybe A and B go here. I'm going to check my notation on that. I might be off slightly. The function f of x and the delta x, when those delta x's become so tiny that they're basically 0, we're going to call them dx's. And so that's why this integral gives me the area underneath that curve. So that's the idea of integration giving me the area under the curve. Thank you for that question. That was a great question. There are lots of great questions still coming in. But we are just about out of time. Somebody wants me to explain a negative plus a negative is a positive. It's not. Did you mean times? If you turn around and you turn around again, you're facing the same direction. I never did a ratio test for Emily. Emily, I hope you're hanging out. We're going to do a quick ratio test to wrap this up because I promised you a ratio test problem and I'm going to deliver on it. So let's say we want to figure out the sum as n goes from 1 to infinity of 1 over 2n factorial. We want to know if this converges or diverges. The idea of the ratio test is we're going to make this variable called rho, kind of looks like a p. That is equal to the limit as n goes to infinity of the next term divided by the current term. So in this case, the next term is 1 over 2, the next term is n plus 1 factorial divided by the current term, 1 over 2n factorial. Technically, this is in absolute values, but everything's positive here, so it doesn't matter. I'm going to simplify this by multiplying by the reciprocal. So we have the limit as n goes to infinity of 1 over, this is 2n plus 2 when I distribute, factorial, times, this is 2n factorial over 1. What's nice about factorial is it counts down. It's very predictable, which is why the ratio test is so nice. So we're going to have 2n plus 2 in the denominator. And it's going to get multiplied by 1 less, which is 2n plus 1. And then it's going to get multiplied by 1 less, which is 2n, and that's going to count down factorial all the way. Well, we've already got a 2n factorial in the numerator, which is really nice because now those 2n factorials divide out. We're just about out of time, so I'm trying to move fast, and I forgot my limit. As n goes to infinity, notice now everything's out of the numerator, and as n gets huge, we get a huge number times a huge number, which is a huge number. This is bad notation. We can't do division by infinity, but you get the idea. 1 divided by huge is going to basically become 0. If the row that you end up with is smaller than 1, the series will converge. If the row that you end up with is bigger than 1, the series diverges. If it equals 1, we don't know anything, and the test has kind of failed us. But we are just about over time, or maybe even a little bit over time. So I want to give a huge thank you to all of you for coming and joining us. Your engagement and questions have been amazing as I share my love of mathematics, of calculus with you. You have made this a lot of fun. Remember, Chegg is here to support you 24/7 with all of your questions. So make sure you're following Chegg on TikTok, on Instagram, on YouTube, on Twitch. Follow them everywhere. Make sure you scan this QR code so you have the schedule of the upcoming lives. I am moving to Thursdays at 4:15, so I hope you can join us for a calculus review at that time. But until then, happy studying. Thanks for